Hello my dear stars, welcome to the class. Let's have a look at what we are going to learn in this session. In this session, we are going to discuss one of the very important theorems popularly known as the Pythagoras theorem, as well as we'll also discuss its applications. Let's begin, okay? This theorem, that is Pythagoras theorem, also known as Bode-Dayan theorem, okay? So to prove Pythagoras theorem, we will use another important theorem. Let's have a look at its statement. Theorem: if a perpendicular is drawn from the vertex of the right angle of a right angled triangle to the hypotenuse, then triangle on both sides of the perpendicular are similar to the whole triangle and to each other. Got it? If a perpendicular is drawn from the vertex of the right angle of a right angle triangle to the hypotenuse, then triangle on both sides of the perpendicular are similar to the whole triangle as well as each other. Clear? So the statement of the above theorem we use to prove Pythagoras theorem. Okay. So here you can see the great famous mathematician Pythagoras. Here it is another important point to you. Bode-Dayan theorem. Pythagoras theorem was earlier given by an Indian mathematician Bode-Dayan, so about 800 BC, in the following form. What was that? The diagonal of a rectangle produces by itself the same area as produced by its both sides, that is length and breadth. Okay, this is equivalent to Pythagoras theorem. So in another form, you can see the famous Indian mathematician Bode-Dayan here. Okay, now let's prove Pythagoras theorem by using the concept of similarities of triangles. Earlier you might have known Pythagoras theorem as well as its proof, but here we will prove Pythagoras theorem by using similarity concepts. Okay, let's begin. State and prove Pythagoras theorem or Bode-Dayan theorem. Here it is the statement. In a right angled triangle, the square of the hypotenuse is equal to the sum of the square of the other two sides. What Pythagoras theorem saying? In a right angled triangle, the square of the hypotenuse is equal to the sum of the square of other two sides. Clear? Let's prove this. So given a right angled triangle ABC, right angled at B. So according to this information, here we have taken a right angled triangle ABC, right angled at B. So to prove AC square equal to AB square plus BC square, that is square of the hypotenuse is equal to sum of the square of the other two sides, that is AB square plus BC square, right? AC square is equal to AB square plus BC square. To prove this, we need little modification in the diagram according to the statement. Okay, let's construct. Draw BD perpendicular to AC. Here we drew BD perpendicular to AC. Okay, now this is the proof. Since ABC is a right angle triangle and BD perpendicular to AC, then by known theorem, which we have already discussed in the previous slide, what it is saying, a perpendicular is drawn from the vertex of the right angle of a right angled triangle to the hypotenuse, then triangle on both sides of the perpendicular are similar to the whole triangle and to each other. So this triangle is similar to this triangle as well as these two triangles are similar to the whole triangle. Okay, this is what this theorem is saying. Clear? Now, so from this we have triangle ADB. Triangle ADB is similar to triangle ABC, that is by AA similarity criterion, or we can say from the above theorem. And triangle BDC, triangle BDC is similar to again triangle ABC, again by AA similarity criterion. Let us take this is equation number 1 and this is equation number 2. Then from equation 1, since these two triangles are similar, we know corresponding sides are proportional. So then we get AD over AB is equal to AB over AC. We can cross multiply here. Then we get AD times of AC is equal to AB square, right? So then AD times of AC is equal to AB square. Let us take this is equation number 3. Now from equation 2, that we have got triangle BDC similar to triangle ABC, right? So since these two triangles are similar, we know corresponding sides are proportional. So then we get DC over BC is equal to BC over AC. Again on cross multiplying, we get DC times of AC is equal to BC square. So DC times of AC is equal to BC square. Let us take this is equation number 4. Now on summing up equation 3 and 4, adding equations 3 and 4, we get, adding both left hand side parts as well as right hand side parts, AD times of AC plus DC times of AC is equal to AB square plus BC square. Again from these two terms we have AC common. We can take AC common, then we get AD plus DC times of AC is equal to AB square plus BC square. Again look at here, AD plus DC. AD plus DC together what? AC, right? So we can replace with AC. So AC times of AC is equal to AB square plus BC square. Again AC times of AC is nothing but AC square, right? AC square equal to AB square plus BC square. This is what we need to prove, right? So hence it is proved. Clear? That is, the square of the hypotenuse in a right angle triangle is equal to sum of squares of other two sides. You can look at here. This is what the Pythagoras theorem is. Is it clear? This is it.